Okay, class. In the previous video, we talked about how you can actually have more than one valid Lewis structure, but they may not be the same energy. They may not be equally stable. And we used formal charges to determine which was the more stable of the species. Now we're getting into a concept called resonance. This is a very important concept that you will see, especially if you go on to organic chemistry in the 200 level and above. So, sometimes we can write more than one different but still valid structure for a given molecule or ion without changing which atoms are bonded together and with similar formal charges. That is, the formal charges are all optimized in all of the structures. In such a case, the true structure of the molecule or ion is actually a blend of all possible structures. Now, there's a lot going on in that paragraph, so we're going to unpack it a little bit. We draw all of these possible structures as resonance structures with brackets around them and a double-headed arrow. Between each of the structures. Yes, earlier we put brackets around polyatomic ions. But now if we have resonance structures, we're also going to do it with a double-headed arrow between them. And then don't forget that if it's a charged species, we also have to have the charge. So as I say, there's a lot going on up there, but I think when we do an example, it will make more sense. So here's example, or exercise A. Draw all possible resonance structures of the nitrate anion. So we know that nitrate, NO3 with a minus charge. I'm going to draw a Lewis structure of nitrate. So nitrogen is valence of 5. 3 times oxygen equals 3 times 6 equals 18 more electrons. And then add 1 for the charge. 18 and 19 is 24. Valence electrons total. So here's my first structure. Nitrogen is less electronegative than oxygen, so nitrogen is in the center. Remember, these are Lewis structures, so I don't worry about three-dimensionality. So I've drawn my skeleton. There's 2, 4, 6 electrons that I've already distributed, which leaves 18. Distributing them equally to the terminal atoms, 2, 4, 6, 8, 10, 12, 14, 16, 18, and I've used them up, right? And now we notice that I've used up all of my electrons, but nitrogen is still not octet satisfied. So I need to shift to share a pair of electrons. And now you will notice the same way that we saw earlier when we were doing formal charges, we have a choice. I can pull an electron pair from any one of these oxygens, but energetically they are all identical. So if I pull this electron pair, I'll have a double bond there. But I could just as easily have pulled it over here, in which case I would have the double bond there. Or I could have pulled one of these electron pairs to have a double bond there. So I'm going to get 3 valid Lewis structures of the nitrate ion, and each of them will have a double bond, but the double bond will be in the three different positions. So don't forget my brackets, because it's an ion. And I'm going to have the other Lewis structure of this with a double bond there, and the other one with a double bond there. And remember, I have a double-headed arrow in between each of them. So the other one is going to look like this. Notice that when I have a double bond to the oxygen, I only have 2 lone pairs on it. I don't have all 3 lone pairs if I have the double bond to it. And I have the other structure where the double bond is now going to be down here. Oops. I only want 2 down here. 2 lone pairs. There we go. So there, I have 3 valid Lewis structures. And unlike our previous example with the cyanate ion, now all 3 of these are the exact same energy. If I do the formal charges, you will see that the formal charge for these single bonded oxygens are the same, and the formal charge for the double bonded oxygens are the same. And so I've got 2 single bonded oxygens in each of these, 1 double bonded oxygen in each of these. And so each of these Lewis structures is an identical energy. And so when you have Lewis structures that are valid Lewis structures of identical energy, then we can call them resonance structures. So these are the 3 resonance structures of the nitrate anion. Now, something very important about this, about resonance forms. Even though I have drawn nitrate as 3 different resonance structures, in reality, nitrate does not exist as any of these. Nitrate does not spend time in this form and then switch to this form and switch to that form. It does not do that. Instead, the true form of the nitrate ion is a blend of all 3 of them. So if you were to take a nitrate ion into the lab, perform an X-ray crystallography on it to determine the bond lengths, you would not find single and double bonds in it at all. And so you end up with 3 bonds that are the same length, and they're about a bond and a third each. So again, resonance forms represent symbolically valid Lewis structures, but they do not represent the actual structure. In reality, the actual structure is a blend of all of these. Nitrate does not switch between these structures. Okay? All right. With that in mind, we have another exercise. So I'd like for you to do this exercise, pause the video, draw all the possible resonance structures of the nitrite anion. So this will give us an opportunity to practice our nitrate, nitrite pattern, nomenclature pattern for the nitrite anion. So go ahead and pause the video, and when you're done, restart the video, and I'll work through this with you. Okay, I'm assuming that you've given us a shot. Let's take a look at it. Nitrite. 1 less oxygen, same charge as nitrate. So nitrogen is 5 electrons. 2 times oxygen is 2 times 6 is 12. And we're going to add 1 for the charge. So we've got 18 valence electrons total. Nitrogen is going to be in the center. I've just used 2, 4 for my skeleton. So I got 14 left. 2, 4, 6, 8, 10, 12. Oxygens are satisfied. I have 2 left. Where do they go? Have to go in the central atom. I've used all of my electrons. Okay. Nitrate is still not satisfied. I'm going to have to shift to share. And now you can see why I end up getting resonance forms, because I could have shifted from here or I could have shifted from here. In fact, I'm going to get both forms. So I'm going to shift that pair there, and that gives me that resonance form. And then in the other one, I'm just going to shift from the other side. So my double bond will be here. In both cases, I have a lone pair on that central nitrogen. So there are my 2 resonance structures for the nitrite ion. Does nitrite spend any time in either of these structural forms? No. The real nitrite structure is a blend of these 2, where that double bond does not really exist in one position or the other. It is actually smeared out or spread out over both of those positions. And that's resonance. So to review, resonance forms are when you have valid Lewis structures that are of equal energy. We have to put a bracket around them even if they are not an ion. In this case they were, but even if they were not an ion, we would put brackets around them. Of course, if it's charged, we put the charger there. And between each resonance form, to show that there is an interblending, we have a double-headed arrow. This is not 2 arrows. It's not this. It's this. Okay? Between each of the forms, just like that. And that's how you deal with resonance. Generally, resonance is a form of stabilization. It's a way that a species can stabilize itself by smearing out some of its electron density to other positions. When we get onto organic chemistry, resonance stabilization becomes a very, very important concept. But you'll learn more about that much later. That's enough for now. Thank you.